Now, next is the, you can see, ligands. Those chemical species which can donate lone pair of electrons to the central metal atom or ion are called what is there now? Ligands. If ligands are 4, then shape may be tetrahedral, with sp3 hybridization, or a square planar with dsp2 hybridization. If ligands are 6, then shape is octahedral with sp3d2 or d2sp3 hybridization. So there must be some difference between sp3d2 or d2sp3 hybridization. We will discuss when I will discuss the valence bond theory. Then we will discuss in detail. Then coordination number. Total number of ligands containing lone pair of electron is called coordination number. It can be 4 or 6. So I have already explained, if coordination number is 4, then the shape may be tetrahedral with sp3 hybridization, or if we can say coordination number 4, then the shape may be a square planar, then dsp2 hybridization. But if coordination number is 6, then there is no confusion over the shape. It is always octahedral, and hybridization may be sp3d2 or d2sp3 depending upon the types of the ligand. Right? Then you can see types of ligands based on denticity. Now, types of the ligands based on denticity. Donation capacity based on denticity. First is the unidentate, undentate, dentate, mono, undentate, monodentate ligands. Such ligands contains only one donor atom. For example, ammonia is the best example there. It has a lone pair of the electron. Water, lone pair and lone pair, right? So you can say OH negative, cyanide negative, PS3 lone pair, fluoride, chloride, bromide and iodide. That means halides. All contains, maybe chlorine contains 4 lone pair, 1, 2, 3, 4, 5, 6, 7 and 8. But atom is only one. So it is monodentate ligand. It may have 4 lone pair, 3 lone pair or 2 lone pair, doesn't matter. But the depends upon the number of atoms. So these all are called as monodentate or unidentate ligand. Now second is the bidentate ligand or didentate ligand. Bidentate ligand. Such ligand contains 2 donor atoms. For example, here oxalate ion. Short, you can write OX2 negative. C double bond OO negative. C double bond OO negative, or it is called as C2O4 2 negative. Oxalate. Then it is known as ethylene diamine. In short, it is EN. The structure, you remember it, CH2, NH2 having lone pair, and CH2, NH2 having lone pair. So it is known as ethane 1,2 diamine. So either you can use ethylene amine or in short EN or ethane 1,2 diamine, because it contains 1 donor atom and other donor atoms. Here it is the donor atoms, here it is the donor atoms. So oxalate and EN are the best example to explain bidentate ligand. Now C is the polydentate. These are very few in numbers and rarely used. More than 3 donor atoms, more than 2 donor atoms are known as polydentate ligand. The best example is the EDTA4 negative. What is EDTA? Ethylene diamine tetra acetate, TATE. Right, how do you write the structure? Tetraacetate. First you write ethylene diamine CH2 COO negative, CH2 COO negative, COO negative, COO negative. So how many donor atoms? 1, 2, 3, 4, 5 and 6. So these are called as polydentate ligand. Ethylene diamine tetraacetate. These are called as polydentate ligand. Now, based on the charge, because ligands are very broader term in coordination chemistry. You remember the ligand on the basis of the charge: anionic ligand, cationic ligand, and neutral ligand. It will help you in writing the IUPAC system of nomenclature in coordination chemistry or inorganic chemistry. So, types of ligands based on charge. First is the anionic ligands. Cl negative, chlorido. Br negative, you can say bromido. Iodine negative, iodido. Iron halido. X negative, chlorido, bromido, iodido. It has a separate system of nomenclature as per the 2004 IUPAC system of nomenclature for inorganic compounds. OH negative, hydroxido. Now sulfato, PO4 3 negative phosphato, C2O4 2 negative oxalato, EDTA4 negative ethylene diamine tetraacetato. You have to write the full name. EDTA means ethylene diamine tetraacetato. Then next is the you can see H negative hydrido, right? CO3 2 negative carbonato, NO3 1 negative nitrato. Then some ligands contains 2 donor atoms, ONO1 negative, it is nitrito, and there you have to express like donor atoms. But if structure is NO2, it is the nitro, and you represent like this, CN1 negative cyano or cyanido, iso cyano, and CNS, it is thiocyanato, NCS, isothiocyanato. These ligands are, these ligands are known as NB dentate ligand. Such ligand contains 2 donor atoms, but at the time they can donate only 1 lone pair of the electrons, known as ambidentate. Thiocyanato, isothiocyanato, nitrito, nitrocyano, isocyano. We have to remember all these. Now come for second type of the ligand, is called as what ligand? Cationic ligand. These are very few in numbers and rarely used. NO positive, NO2 positive, NS2, NS3 positive, nitrosonium, nitronium, hydrazinium, etc. These are known as, positively charged ligand. Nitrosonium and nitronium. Be careful in writing the name and all that. C is the last part, is the neutral ligand. They do not carry any charge. If NS3 is there, here we have to use the word amine. AMMINE, amine. Water, either you can use aqua, or you can say it is the aquo. CO, carbonyl. CS. CS is, what is that? Sulfur is termed as thiocarbonyl. NO, it is nitrosyl. NS, nitrosyl. And then you can say urea. NS2, C double bond O, NS2, urea. NS2, C double S, NS2, it is known as thiourea. And then other examples are, in case of the neutral ligand, is that C5H5 and pyridine, PH3, phosphine, C6H5 whole thrice P, it is the triphenyl phosphine. In short, it is TPP. This is the triphenyl phosphine. And then next is the methylamine. CH3NH2 is the methylamine, and CH2NH2, CH2NH2, it is the ethane 1,2 diamine, or EN, ethylene diamine. CH3 is known as methyl, C2H5 is known as ethyl, C6H5 is known as what is that? Phenyl. So these are the types of the ligand: positive ligand, negative ligand, positive ligand, and the neutral ligand. Now they will help you in calculating the oxidation number that is very much given in your exercise question. For example, how to calculate the oxidation number of the central metal atom. For example, K4 FeCN6. Now let you put under down, always you calculate the oxidation state of the central metal atom. That is very much assigned in question. So iron is taken to be X, potassium +1 charge. You remember in 11th class, alkali metal, sodium, potassium, +1 oxidation state, and alkaline earth metal, calcium, beryllium, magnesium, +2 oxidation state. It's alright? Okay. +1 into 4, +X, cyanide contains 1 negative charge. Sum is taken to be 0, +4 +X, -6 equal to 0, X is equal to what is that? +2. So you have to use in the stock notation in parenthesis. This is known as stock notation. You remember in the redox reaction in your previous class. So here you write Roman letters in the parenthesis, a small bracket in mathematics, like that. So if I say CO, NH3 bromine and SO4. So tell me, cobalt is taken to be X, ammonia is the neutral ligand, bromine -1 and sulfate -2, sum is taken to be 0. So X -1 -2 equal to 0. So X equal to what is that? +3. Let you represent in the Roman letter in parenthesis. Now I give you other example to calculate the oxidation number, like Zn NH3 2 positive. Let you taken to be X plus ammonia is a neutral ligand is equal to +2. So X is equal to +2 in a stock notation like this. I give you other example, NaCO6. So this is cobalt, central metal atom, carbon big, oxygen small, but it is carbon monoxide, but here you say carbonyl. CO, both are capital. Therefore take the cobalt X, sodium +1 +X +0 into 6 equal to 0, because carbonyl is a neutral ligand, so X is equal to -1. So minus you will get very rare, rarest of the rare example, otherwise it is not minus. If it is minus, then you can put -1 sign, or sometimes it may be 0. For example, Zn H2O6. Let it be X +0 into 6 equal to 0. So X equal to what is that? 0. So oxidation state can be 0, negative or positive, but here you will get very rare chance to get the negative oxidation state. But you apply the stock notation and then you put the right answer. It will help you in writing the IPAC system of nomenclature.